Your corgi puppy, with a mass of 10 kilograms, decides to jump into a laundry basket full of clothes with a total mass of 3 kilograms. You decide to take this opportunity to get some laundry done and play with the puppy, so you decide that you want to push the puppy in the basket with a constant force so they move at 1 meter per second 5 seconds later. The basket and the floor have a coefficient of kinetic friction of 0.4 and a coefficient of static friction of 0.5. How much force is needed to push the puppy in the basket? The first important thing to do in solving this problem is to establish what our system is. The corgi is 10 kilograms on its own, and the loaded laundry basket is 3 kilograms. Together, they are 13 kilograms, and we assume that the corgi plus laundry setup is a single point of mass, which is thus our system. Now we can draw a free body diagram for the system. We have the normal force, which is directed upwards to counteract the force of gravity. These two are of equal magnitude but have different directions, so because they cancel each other out, F net is 0 in the y direction. In the x direction, we have the force of the push, which is what we're trying to find. The force is in the negative x direction, since we're looking at the corgi plus laundry's movement towards the left. Then we have the force of friction, which is in the positive direction towards the right to counteract said movement. Now on to the fun math. First, let's establish our constants. Since we'll be using the momentum principle, let's find both our initial and final momentum. At first, the corgi plus laundry aren't moving, so initial velocity is 0, which means initial momentum is also 0. The final velocity at which we want our corgi plus laundry setup to move is negative 1 meters per second, so this makes our momentum negative 13 kilogram meters per second, which equals the mass of the system, 13 kilograms, times the velocity, negative 1 meters per second. To find our F net, we can use the derivative form of the momentum principle, which states that the instantaneous time rate of change of momentum of an object is equal to the net force acting on the object. This derivative form is useful to us when we know the rate of change of momentum. In our case, we want to achieve a change in momentum of negative 13 kilogram meters per second over a 5-second period. The change of momentum is equal to our final momentum, since our initial momentum was 0, so calculating delta P, negative 13 minus 0 is negative 13 as well. When we divide negative 13 by 5, we get negative 2.6, which is our F net in the x direction. Our work doesn't stop there. Now that we have F net, we can use it to find the force of the push and the force of friction in this problem. We plug in what we know, which is just negative 2.6 newtons right now. At this time, we can find the frictional force, which is the coefficient of kinetic friction, since the corgi plus basket are moving, times the normal force. Looking back at the y direction, we know that the normal force and gravitational force cancel each other out due to equal magnitudes in opposite directions. So we can say that the normal force equals mg, which is 13 kilograms times 9.8, equaling 127.4 newtons. And we sub this in to find that the normal force is 50.96 newtons. To solve for the force of the push, all we do is isolate it by subtracting both sides by 50.96, and we get that the force of the push is negative 53.56 newtons. But is this force enough to get the corgi plus basket moving in the first place? We check this by finding the maximum static frictional force, which shows the threshold needed to move an object. So, we set up the equation here, which is similar to what we did for the kinetic frictional force. We sub in our knowns, and we find that the maximum static force to hold the corgi plus basket in place is 63.7 newtons, so we need negative 63.7 newtons or more to push the corgi plus basket in the negative x direction. Here is a summary of what we found so far regarding the forces we need to move the corgi plus basket at all, and to keep them moving to reach 1 meter per second in 5 seconds. And here's our newly improved free body diagram with all forces included.